We will now discuss hypothesis test for population mean when the standard deviation is known, using the method for p-values. To measure how strong the evidence against H0 or null hypothesis is, we will compute a quantity called the p-value. Now, we calculate the p-value differently based on if it's a left-tailed, right-tailed, or two-tailed test. The different ways we calculate the p-value are described here. For a left-tailed p-value, the p-value is just the area under the normal curve to the left of the test statistic, or the z-score that we calculate. For a right-tailed p-value, the p-value is the area under the normal curve to the right of the test statistic, or z-score. And then finally, for a two-tailed p-value, the p-value is the sum of the areas under the normal curve to the right of the test statistic, z, and to the left of the test statistic, negative z. So that's the area to the left of negative z and to the right of z. Now, instead of calculating these separately, one thing we can use to our advantage is the normal curve is symmetric. So we could also just find the area to the left of the negative z and then double that area, and we'll get the area to the left plus the area to the right. And one key detail to keep in mind is that the smaller the p-value, the stronger the evidence we have against our null hypothesis. So let's say we have a test whose null hypothesis is that mu is 30, compared to the alternate hypothesis that mu is less than 30. Now, just from this phrasing, is this a left, right, or two-tailed? Because mu is less than 30, this is a left-tailed. The test statistic is z is negative 1.28, so here they've calculated this for us. So if I'm going to draw my visualization here, I've got my negative 1.28 to the left of the middle, which is at 0. And we know my p-value is the area to the left of this z-score. Now, in previous lessons, we took a z-score, and from our cumulative normal distribution chart, we were able to find area to the left of that score. And that's what we're going to do exactly here. So looking at our cumulative normal distribution chart, I look for a z-score of negative 1.28, so I'm going to look at the negative 1.2 row, which is all of these. And I'm going to go to the 0.08 column, and then zooming in, we see the area to the left of that is 0.1003. So my p-value is just the area to the left of that score, so 0.1003. Next, we have a test that has our null hypothesis mu is equal to 6, compared to the alternate hypothesis mu is not equal to 6. Now, just based on this, is this a left, right, or two-tailed test? Because it's mu not equal to, we know this is a two-tailed test. We've been told our test statistic is 0.75. Because it's a two-tailed test, I could draw my normal curve. And for this normal curve, I know I've got two tails, the negative version of the z-score, negative 0.75, the positive version of the z-score, and then I know my p-value is the area to the left of the negative value plus the area to the right of the positive value. Now, my chart, keep in mind, only tells area to the left. So while we could use the chart plus some other information that we have to find area to the right, if you remember in our previous lessons, we would actually have to take an additional step to do so. Because the chart is set to give us area to the left of a value, I recommend that we find the area to the left of the negative 0.075, and since it's symmetric, we know it will be the exact same value here, so we can just double that. So I look at negative 0.7. That would be that row. 0.05 is this column. So we see our area is 0.2266, but as this is symmetric, the area to the right is the same value. So then my p-value is just these two added together, or equivalently doubling one of them. So p is 2 times 0.2266 Type that in the calculator and we get 0.4532. Now if we had the same setup, but now our test statistic was instead of 0.75 a negative 2.20, we're still dealing with our two-tailed test. So I mark my negative z-score negative 2.20, my positive z-score 2.20, area to the right of that one, area to the left of this one. I know that I can find the area to the left here and then double it. So for negative 2.2, this is our row, this is our column, so we get 0.0139 as the area to the left. And by symmetry, we have that same area to the right. So our p-value is just twice the area to the left. Type that in the calculator and we get 0.0278. Now our next question, which provides stronger evidence against H0, the z-score of 0.75 or the z-score of negative 2.2? The answer to this comes from what we have highlighted here at the top of the screen. We know that the smaller the p-value, the stronger the evidence. So between a p-value of 0.4532 and a p-value of 0.0278, I think we'd agree that that's the smaller value. This smaller p-value provides a stronger evidence, and that's associated to a z-score of negative 2.2. So what have we done so far? We've introduced the basic definition of p-value. We've calculated a few different p-values, and then we also focused on the idea that the smaller the p-value, the stronger the evidence against H0. Now let's take a few more notes about p-values. As we saw previously, the smaller the p-value, the stronger the evidence, repeated because it's important. Now the p-value is the probability under the assumption that H0 is true, that the test statistic, or z that we're going to calculate, takes on a value as extreme as or more extreme than the value actually observed. Now one thing to keep in mind is the p-value is not the probability that the null hypothesis is true. That is an example of something that it is not. It is not the probability a hypothesis is true. So in this example below, it says if p is 0.02, which is the best conclusion? So here we've got multiple choice. Option A, option B, option C, option D. Let's read through these and think which is the best conclusion. Option A says the probability that H0 is true is 0.2. So it's saying the probability that the null hypothesis is true is the p-value. But right here it said the p-value is not the probability the null hypothesis is true, so we can immediately cross out A as incorrect. Moving on to B, if H0 is true, the probability of obtaining a test statistic more extreme than the one already observed is 0.02. Now if we look at the phrasing of this second point, that matches exactly what we found in B. So I think B is our answer. Let's just quickly read through C and D just to verify. The probability that H1 is true is 0.02. We never saw anything like that in terms of what the p-value is, so C is out. And if H1 is true, the probability of obtaining a test statistic more extreme than the one actually observed is 0.02. We need to watch the detailed difference between B and D. H0, H1, but if we look at the actual definition, it was about H0, so that is why D is out. So B is our correct answer. Now that we've introduced the basics of the p-value, we have one more thing to introduce before we can get through the steps of solving the hypothesis test when using the p-value method, and that next idea is the significance level alpha. Now the most commonly used values of alpha that you'll see is 0.05, but other values can be used as well. After 0.05, 0.01 is the next most commonly used. Now when we use the p-value method to evaluate our hypothesis test, we make our decision whether to reject H0 by first getting a significance level alpha between 0 and 1, then computing the p-value, and we talked about how to do this previously in this video, And then how do we make our decision? Well, if the p-value is less than or equal to alpha, we reject h-naught. Here we would say h-naught is rejected at the alpha level, so we would list what level we rejected it at, or we could equivalently say the result is statistically significant at the alpha level. If p is greater than or equal to alpha, we do not reject h-naught. So in order to make your decision whether to reject or fail to reject h-naught in the p-value method, you calculate the p-value, you look at your alpha given, and if p is less than or equal to alpha, you reject. If p is greater than alpha, you do not reject. So let's practice this reasoning. Let's say that a hypothesis test is performed. Now our alpha level here is 0.05. If the p-value is 0.08, so that was already calculated, do we reject h-naught? Well, let's see. Our p-value of 0.08 is actually greater than our alpha value of 0.05. And they say when p is greater than alpha, you do not reject, or we fail to reject. Okay, since we do not reject h-naught here, the results are not statistically significant because we failed to reject. So we'll say no here. Moving on to C, if instead the p-value was 0.03, is h-naught rejected? Well, for this new p-value, it is less than or equal to our alpha of 0.05. Following that, we say that h-naught is indeed rejected at the alpha level. If the p-value is 0.003, are the results statistically significant? Yes, following this reasoning. Now, if our alpha was at the 0.01 level, would we reject it for the p-value of 0.02? Well, for the p-value of 0.02, that is greater than the alpha value of 0.10, and if the p-value is greater, we reject, we do not reject, fail to reject. Okay, what do you think if the p was 0.005 and alpha was 0.1, what would occur? So in this case, the p-value would be less than or equal to our alpha, in which case we reject at that alpha significance level. Now the next example is just another example like we've just seen, so I'd encourage you to pause the video and attempt this on your own, unpause to check your work. So alpha was 0.01. If p was 0.08, that is less than or equal to the alpha value. And we know if p is less than or equal to alpha, we do reject h-naught. If instead my p-value is 0.5, that's clearly greater than my alpha value, in which case we would fail to reject h-naught. So in this next page, we go over the steps to perform a hypothesis test for a population mean with sigma known using the p-value method. First, you quickly check that the assumptions are met. Do we have a simple random sample? Is the sample size large, i.e. greater than 30, or normally distributed? And if both of those are met, then we continue on to the steps to go through our hypothesis test. Let's go to that section. So here on the screen, you can see all 6 steps listed out. I encourage you to definitely have this note packet printed. As you can see in our online course, it's posted. And have this list next to you as you go through the homework problems. Now I'm going to zoom in so we can see them a little bit more clearly, but we won't be able to see all steps at once. Step 1 is just like before with the critical value method. State the null and alternate hypotheses. And we've been told, remember what happens if you're in a left tail, right tail, or two-tailed. Okay, next choose a significance alpha if it's not already provided. So we've got step 1, step 2. Compute the test statistic z, same as before with the critical value method. Now where the critical value method and the p-value method differ is we compute the p-value of the test statistic. So remember, based on whether you know if you're doing left, right, or two-tailed, you would compute the p-value in a different way because you've got your z-score right. And if it's a left-tailed test, The p-value is the area to the left of the score, which comes straight from our cumulative normal distribution chart. We've been dealing with that for a bit in these last few lessons. If instead you were dealing with a right-tailed test, here's your z-score that you just calculated in step 3. Well, the area is the area to the right of that z-score. Now, a word of caution here, when it's the area to the right, keep in mind that the chart gives you automatically the area to the left. So when you look in the chart, it's actually going to give you this area, which is not what you want. So then keep in mind, you could do 1 minus that area, and you'll get exactly what you're looking for. Because we know the total area is 1, so if they've given you the wrong side, just say 1 minus that, and you'll get what you're looking for. Finally, if we're dealing with a two-tailed test, we know it's the area here plus the area here. Based on symmetry, I can just find the area here and double it. So based on if I'm doing a left, right, or two-tailed, I'll do one of these methods to find the p-value. Step 4 is complete. And then we interpret the p-value. Remember, we reject h0 if the p-value is less than or equal to alpha. And then finally, step 6, state the conclusion, rephrase in terms of the wording of the problem. So let's go through these steps in our next examples. According to the National Health Statistics reports, the mean height for U.S. men is 69.4 inches. A sample of 300 men, so our N here is 300, between the ages of 60 and 69, the mean height there was found to be 69 inches. So my sample mean, 69. Public health officials want to determine whether the mean height, mu, for older men is less than the mean height of all adult men. Based on this phrasing, we need to write out our appropriate hypotheses. So we have our null hypothesis and our alternate hypothesis. I would encourage you to take a moment, pause the video, and think about what you would claim to be your null and alternate hypothesis here. Remember, you're getting your claim from the wording of the problem, so pause and think about it. Okay, we know h0 is always that our mean is equal to the general value that's reported, 69.4. But we're interested if in this sample of older men, the mean height is actually less than that overall mean. So I'm going to have mu is less than 69.4. And here, just from this, we know automatically we're dealing with a left-tailed test. That's important to focus on because it will affect how we calculate our p-value. So A is done. B, assume the population standard deviation, so I'm going to record that here, is 2.84. Compute the value of the test statistic, so our z-score there, and state a conclusion using the alpha at 0.01 level of significance. And keep in mind, while I could solve this problem using the critical value method, which was discussed previously, or the p-value method, which is the focus of these last few minutes, I'll get the same answer. Now, just since we haven't seen it illustrated, I'm going to go with the p-value method for this problem, although I could choose to do the critical value method if I preferred. Now let's get our steps on the screen for this particular hypothesis test using the p-value. So looking at our steps, we've already got step 1 done. We've got our null and alternate hypothesis. We see that we are left-tailed. Significant level was already given for us. I'm going to record that here. Alpha was 0.01. Next, I calculate the test statistic. So z is my x bar minus our mu naught. And keep in mind the mu naught is this value, divided by sigma over the square root of n. So for this particular problem, this will be 69 minus 69.4 over 2.84, which was then divided by the square root of 300. Now I'm going to type this into the calculator and round to 2 decimal places. When we round to 2 decimal places, I get negative 2.44 as my z value. Now I know this is a left-tailed test, so I'm just going to draw a quick picture to help me visualize as I make my p-value. I've got my value before the peak of the curve, and I know the p-value is this area to the left. Now that's exactly what the chart would tell me. So if I look at my cumulative distribution chart, at negative 2.44, here's my negative 2.4 row, my 0.04 column, and we see the area. It might be hard to see on the screen, but if you are looking at your own chart, you'll see that it is 0.0073. So that is my p-value. So my p-value is 0.0073. So we've completed step 3, we've completed step 4, and now we interpret the p-value. Remember, it says reject h0 if p-value is less than or equal to the significance level. So my p-value here, compared to my significance level, indeed it is less than my significance level of 0.01. So I can be prepared to reject h0. So all that's left is step 6, which is state the conclusion. And in case it helps us, I've got our flow chart here that we've seen before. In our case, we are rejecting h0. So that means we need to describe that h0 is false and h1 is true. So looking back at the problem, what was true? What was true that we were wanting to measure is that the mean height for the older man was indeed less than the mean height of all adult men. So now that we've stated our conclusion in terms of the phrasing of the original problem, we are done. So our next example says that technicians are testing a scale by using a weight that is known to weigh exactly 1,000 grams. Now they weigh this weight on the scale 50 different times, and they read the result each time. Of the 50 scale readings, they have calculated to have a sample mean of 1,000.6 grams. Now the key thing here is the scale is said to be out of calibration if the mean scale reading differs from 1,000 grams. So what we have highlighted here is how we know if it's out of calibration or in calibration. The technicians want to perform a hypothesis test to determine whether it's out of calibration. Said in another way, whether the scale reading is different from 1,000 grams. State the appropriate null and alternate hypotheses. Now again here, I would encourage you to pause the video and attempt part A on your own. This is a good way to check your understanding thus far. So we know the null hypothesis begins with our mu is equal to, okay, the value that we're sure about is the 1,000 grams. And we really care about whether it's measuring different from. Now, different is the idea of not equal to. So my alternate hypothesis is mu is not equal to 1,000 grams. Now for part B, it says assume the population standard deviation to be 2 inches. Compute the value of the test statistic, and then state the conclusion using an alpha 0.05 level in significance. And although we could use this using the critical value method, so that we're on the same page, let's just work it with the p-value method. Now you've seen an example previously of how to do these problems. You've got the steps listed on your notes. Pause the video now and attempt this on your own. Then when you finish, unpause to check your work, and you can see step by step if you got it correct at each step. If not, you can isolate where the error happened and correct it with the next solution. So I'm first just going to draw out some of the details. We know they weighed it 50 times, so n is 50. The sample mean is 1,000.6. My mu naught is 1,000. Sigma, standard deviation, is 2. And my alpha value is 0.05. So I know if I'm looking at my steps, step 1 I've completed because I have my null and alternate hypothesis. Alpha was given, step 2 is completed. Next up, I'm going to do my test statistic. Z is equal to the sample mean minus our mu naught over sigma divided by the square root of the standard deviation. So for us, that is 1,000.6 minus 1,000 over my sigma of 2 divided by the square root of 50. Now, one thing I'm going to note here, since it's not equal to, I know this is a two-tailed test. Typing this into the calculator and rounding to 2 decimal places, we would find 2.12 as our test statistic. Now, since we're in a two-tailed test, I know that I've got my normal curve, and this is really my plus or minus because we're at the z-score. So I've got my negative 2.12, my positive 2.12, and the p-value is the area before the negative 2.12 plus the area after. Now I know via symmetry I can simplify this by just calculating the area before the negative 2.12, which is how the chart is perfectly set up, and doubling that. So let's look at the chart. So negative 2.12, I've got my negative 2.1 row, 0.02 column, and we see the area to the left is 0.07017, which is exactly the same on the right because it's symmetric, so I can just double that value. So my p-value is 2 times 0.017, which is a 0.034 as the p-value. Now if we look at our steps, we've got our test statistic, we've got our p-value. All that's left is to interpret. Remember, if the p-value is less than or equal to the test statistic, we reject h0, and then I just have to state my conclusion. So looking here, since my p equal to 0.034 is indeed less than or equal to my alpha value of 0.05, I'm going to reject h0. Now that I know I'm rejecting h0, I still need to figure out how to phrase it in terms of how the problem was presented, because it was presented in context. That's part of stating my conclusion. Now, by rejecting h0, we're saying this is false. We're saying the scale did not measure 1,000. And if the scale did not measure 1,000, then it differs from 1,000 grams, which means the scale is out of calibration. So for this problem, I could just say the scale calibration has shown to be wrong because it's measuring a value different from 1,000 grams. So we've seen how to deal with hypothesis tests for population mean when standard deviation is known in 2 methods, critical value and p-value method. Look over the 2 methods and see and ask yourself, which do I prefer, critical value or p-value, and then just use that method going forward. Now, let's briefly talk about the relationship between hypothesis tests and confidence intervals. We've talked about confidence intervals previously. We've just introduced the idea of hypothesis tests, so we're going to talk about how they are related and different. A confidence interval provides all the values that are plausible at a specified level. What do we mean by specified level? Remember when we were doing confidence interval, it would say something like 95% confidence, 99% confidence. That's our specified level. A hypothesis test tells us how precisely how plausible a particular value is. So it's no longer a range of values, it's a singular value. If we test our h0 mu equal to mu naught versus our alternate hypothesis not equal to mu naught, then if the 95% confidence interval contains mu naught, then h0 will not be rejected. We could know that as our conclusion. If the 95% confidence interval does not contain mu naught, then it will be rejected at the 0.05 level. So in particular, let's use the information in this box to answer our upcoming examples. It says you want to test h0 is mu equal to 4 versus h1 is mu not equal to 4. So far we have the same setup of our null and alternate hypothesis. We've got our two-tailed test. You compute a 95% confidence interval for mu. We know how to do that from previous lessons. And it turns out that the 95% confidence interval is this. Mu can take on values between 5.1 and 7.2. Do we reject h0 at the 0.05 level? Well, our mu value of 4 is outside our confidence interval. It's not in the confidence interval. So we're in this case. it does not contain mu naught, then we will reject H naught at the 0.05 level. Now, say that your friend thinks that alpha value of 0.01 is more appropriate significance level. Now we know an alpha value of 0.01 would correspond to a confidence level of 90%. Can we tell from this confidence interval whether we should reject at this level? Here, we can't tell because what we were given information about is our 95% confidence interval. Now, our alpha was our significance level. So keep in mind this alpha here is the significance level. And we want to quickly describe the relationship between our value of alpha and the probability of a type 1 or a type 2 error. Now, we've seen this chart before, right? We know that if our H naught is actually true, but we end up rejecting H naught, that's a type 1 error. If instead H naught was actually false, but we don't reject it, that's a type 2 error. And then our other two options show correct decision, not rejecting the true H naught or rejecting the false H naught. Now it turns out the probability of a type 1 error is alpha, the exact same alpha of our significance level. So if somebody asks you what's the probability of a type 1 error and you know the significance level, it's just alpha. Now the probability of the type 2 error is what we call beta, and it is a bit more complicated to find. For now, it's enough just to know that the probability of the type 2 error is named beta. Now, one thing we want to keep in mind is the smaller value we choose for the significance level, the less likelihood we have a type 1 error. But at the same time, the smaller the alpha level, the larger the probability of a type 2 error becomes. So by lowering alpha, we lower the risk of type 1. But by lowering alpha, we at the same time raise the risk of type 2. Now, in general, making a type 1 error is more serious than making a type 2 error. So we want to avoid type 1 errors more than type 2. It says a hypothesis test is performed at the significance level of 0.05. What's the probability of a type 1 error? Well, it says the probability of a type 1 error is just the significance level. So our probability of a type 1 error is 0.05. Next up, we have Charlie will perform a hypothesis test at the 0.05 level. Anne will perform the same test, but she'll choose a smaller level, 0.01. If H naught is true, who has the greater probability of making a type 1 error? Okay, so remember, if H naught is true, then to get a type 1 error, we would have to reject a true H naught. And just looking at our box above, it says the smaller the alpha level, the smaller the type 1 error risk becomes. So we could say whoever had the smaller alpha level had the smaller risk. Now reversing that, since they cared about greater probability, we would say whoever had the greater alpha level had the higher risk. So greater alpha, greater risk of type 1. Looking at that, that would be Charlie as our answer because he had the higher alpha level. Now, if H naught is false, what's the greater probability of making a type 2 error? We know that type 2 errors occur when you've got a smaller level of alpha. So for a type 2 error, the smaller the alpha, the greater the risk of type 2. So here, the smallest value of alpha came from Anne. So Anne has the greater risk of making a type 2 error. So as always, if you have questions, don't hesitate to reach out via our campus communication, and I'll be very happy to help you.